Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and in this lecture we're going to use the theory of angular momentum to understand how matter interacts with electric fields. In our previous lecture, we looked at the role of angular momentum in terms of its contribution to the kinetic energy of a free particle. So just to recall, what we showed was that here's the kinetic energy operator for a particle moving in 3 dimensions, the h bar squared over m del squared. And this turns out to break down into a part that just depends upon the distance from the coordinate origin, spherically symmetric, and then a contribution of the angular momentum operator, which is dependent upon the angles that the directions in space that a particle makes. In fact, you're probably familiar with an instance of this in a somewhat different context, and that is for the case of a rigid rotator in space. So in classical mechanics, the kinetic energy of a rigid rotator of mass m and radius r is given by this. It's L squared over 2mr squared. And so if we look at a simple rotating molecule with 2 massive pieces, then we get this expression for the kinetic energy. It's just the square of the angular momentum divided by twice the reduced mass and the distance between these 2 other masses taken as points. And you can easily derive this just by looking at the kinetic energy of the 2 particles as they rotate but are constrained to move at a constant distance. It turns out that this is a rather good approximation for the rotational motions of molecules, which are very important in, say, thermodynamics of gases. The rotational mode of a molecule is sort of the lowest energy mode beyond just simple translation. And the rotational states of molecules are coming into great interest in the particular context of production of ultra-cold molecules for study of quantum gases. So we're going to look at an example that is based on one such molecule, potassium rubidium, and understand what the rotational dynamics for that system are. Also in the previous lecture, we introduced a system of a set of special functions of spherical harmonics, which are generally useful for describing states of angular momentum. Here's a conventional definition, notation, and you can find more information about these in this particular section, the Digital Library of Mathematical Functions. Now, just as you saw that the role of angular momentum for a free particle is very similar to its role for a constrained system of particles, it turns out that for describing angular motion, this set of functions has a sort of universal applicability. It's found in many branches of physics describing wave motion, optics, electrodynamics, theory of elasticity, and so on. And I'm not going to dwell in depth on the properties of these functions, but you should know a little bit about the simple ones and the general things that they make possible. So basically, you can think of these as a set of functions that's useful for describing variations of any type of function defined on the surface of a sphere. So they're defined in terms of the polar coordinates of 3 dimensions, the polar angle theta and the azimuthal angle phi, and the indices, index L, which represents the magnitude of angular momentum, goes from 0 to infinity, and then M, which is a projection of that projection of the angular momentum on a chosen axis, typically the z-axis or the x3 axis, runs from -L to L. Now, if you just open a book and look at expressions for spherical harmonics, they can tend to be a little bit confusing. So I'm going to give you a useful mnemonic for thinking about them. Basically, you can always think of a spherical harmonic in terms of a generalized polynomial. That is, it consists of um, products of the three coordinates x1, x2, x3, where the net power a plus b plus c is equal to L, the index of the spherical harmonic, all divided by an inverse power r to the minus L. So you see this is dimensionless. This is inverse units of length to the nth power. This is units of length to the nth power. And furthermore, the spherical harmonics all obey this relation. So in other words, if you take the Laplacian and apply it to the numerator here, then it vanishes. Now you might ask, how helpful is this? Well, I think you'll see quickly that this enables you to test whether something is a spherical harmonic and even to be constructive in creating your own. So you see, for the low order harmonics, L equals 0, 1, and 2, you can quickly recognize them just by applying the Laplacian. And you can even make your own to suit your own purposes. That is, you can form polynomials that will suit your particular ends at the moment from just more or less arbitrary powers of the three coordinates. So I'd like to also note another important result of this definition is that you see all the spherical harmonics of a degree L have a net power of L in the Cartesian coordinates. And so that means that under inversion of all coordinates, the spherical harmonics either remain the same if L is even, or change sign if L is odd. So for the next few parts of this lecture, we're going to look at an application to discussing the rotational motion of the molecule potassium rubidium. This is one of the great targets for ultra-cold molecule research. Here's a recent paper by one of the leading groups in the field that's accessible through Science magazine, or you look on Google Scholar and find references to this work. Basically, there's a big milestone in making very cold molecules, which are of interest to a wide range of scientific applications, and just technically fascinating and challenging to work with. So the properties of potassium rubidium are well known. The reduced mass of this molecule is given by this number. The equilibrium radius is not that well known at the moment, but we'll take this dominant value of 0.4 nanometers. And one important aspect of this molecule is that it has a permanent electric dipole moment in its body frame. Now, what I mean by that is, if you just hold the molecule in one place, there's an imbalance of charge. There's more negative charge around the potassium and more positive charge around the rubidium. And that means that this molecule acts like an electric dipole when it's exposed to an external field. We'll discuss that momentarily. But when there's no electric field present, then the Hamiltonian that describes the rotational motion of this molecule is just given by this L squared over 2 mu r E squared, where R is the equilibrium bond length. And I've converted that, so that's L times L plus 1 times h bar squared over 2 mu r E squared. And I've converted that to an energy in temperature equivalent units, just because it's convenient for these cold molecule applications. And so you can see that this equivalent temperature, which is basically half the distance between the L equals 0 and the L equal 1 rotational state, is equivalent to 55 millikelvin. Very low temperature, much colder than liquid helium, for example. Now, we use the dipole moment of the molecule as a convenient reference axis. So we're going to describe the orientation of the molecule with respect to some arbitrarily chosen laboratory frame, the X3 axis laboratory frame, in terms of the angle. Well, in terms of a given Cartesian frame, we describe the orientation of the molecule by the angle that its dipole moment makes with respect to the various axes. Now, in the ground state of the molecule, it's the lowest spherical harmonic is just a constant. That's something you should always remember. The first L equal 1 is just either x, y, or x1, x2, or x3, or some linear combination of them. And this means that the dipole moment is oriented randomly in space, so there is no net dipole moment of the molecule when we go to make a measurement of it. It could be in any arbitrary direction. So we're now going to address the question of how we orient and control